on to the second chapter, that is magnetic effect of electric current. So what is this magnetic effect of electric current? When electric current passes through a conductor, a magnetic field will be produced around the conductor. This effect is known as magnetic effect of electric current. So we have to study in detail what about this magnetic effect in this lesson. In the picture that you see in the screen, it is clear about the magnetic flux lines around a bar magnet and that of a solenoid. See, the magnetic field is felt along the magnetic flux lines that you have studied in 8th standard. So the magnetic flux around a bar magnet starts from the north pole and ends in the south pole. The magnetic flux lines do not intersect each other, and the magnetic flux density or the magnetic flux can be seen greater at the poles. So in the figure that you see, the magnetic flux lines around a bar magnet and around a solenoid are depicted. We have to study the magnetic flux lines around a solenoid.
Ørsted's experiment. Danish school teacher Hans Christian Ørsted in the year 1820 concluded a magnetic field is created around a current-carrying conductor. Hans Ørsted placed a compass needle below a wire carrying current. He observed that the needle deflected, showing that a magnetic field is created around the wire. Hans Ørsted repeated the experiment by placing the compass needle above the wire. He observed that the needle deflected in the opposite direction. This experiment indicated that the direction of the magnetic field above and below the wire is in opposite directions. He also observed that if the direction of the current in the wire is reversed, the deflection in the compass needle is also reversed. This experiment shows that the direction of the magnetic field depends upon the direction of current.
So in the video you saw when electric current passed through that straight conductor, the magnetic needle deflected. So why does this magnetic needle deflect? If a magnetic needle has to deflect, then there should be a magnet around somewhere its premises, isn't it? So when there is another magnet near one magnet, the magnet will deflect. So in the figure there was no other magnet given, but there was only a wire through which electricity passed. So by the deflection of that magnetic needle, we can infer that when electricity passed through the straight conductor, a magnetic field was developed around that straight conductor. Due to the presence of these two magnetic fields, the magnetic needle deflected, or due to the mutual interaction of the two magnetic fields, the magnetic needle deflected. So there is a table given there. The completion of the table I will give it in the next class.
Magnetic field around a straight conductor. Magnetic field around a straight conductor can be understood by the following activity. Take a flat cardboard and cover it with a white sheet of paper. In the middle of the cardboard, make a hole and through it pass a thick wire and connect the ends of the wire to a dry cell using connecting wires. Plot magnetic lines of force around the conductor with the help of plotting compass. It is observed that the lines of force are in the form of concentric circles. The direction of the lines of force will be clockwise. The experiment is repeated again, but now the current is passed in the opposite direction as shown in the figure. Then the lines of force will be in anti-clockwise direction. If the strength of the current is increased, then the number of lines of force around the conductor increases. This in turn increases the magnetic strength of the conductor.
In a previous video, we saw that a straight wire carrying an electric current produces a magnetic field in concentric circles around it. In this video, we're going to see how to remember the direction of the magnetic field due to the current. So let's say this pen represents our straight wire carrying an electric current, and let's say the current is running this way towards the tip of the pen. Then we know the magnetic field around it will be in circles. But that can be in two directions. If I use a bangle to represent the magnetic field, then it can either be this way, where on the top the magnetic field is to the right, as you can see by the arrow mark, or it can be this way, where on the top the magnetic field will be towards the left. So how do we remember what direction it's going to be is the question. So a simple rule that we're going to use over here is called the right hand thumb rule. It says that you take your wire and you clasp it with your right hand, not the left hand, right hand, such that the thumb represents the direction of the electric current. So over here, notice the electric current is this way. So my thumb has to point in that direction. Then the four encircling fingers will tell us the direction of the magnetic field. So over here, notice the encircling fingers are telling me that the magnetic field on the top is to the right. And so now I know that the magnetic field has to be this way. It says that on the top, it's to the right. And if the electric current were to reverse, let's say downwards, electric current was downwards, now I would clasp the same conductor with my right hand this way, because the thumb should point in the direction of the current, this way. And so now look at the four fingers. The four fingers are telling me that the magnetic field on the top is to the left. Can you see that? It's to the left. And therefore now the magnetic field is going to be this way. Sometimes you have to figure out the direction of the magnetic field at a specific point around a conductor. For example, again, let's say we have a current carrying wire, which is carrying current in this direction. And I ask you, what is the direction of the magnetic field at a specific point over here to the right of the conductor? How do we calculate that? Well, again, the first step is the same. You use your right hand clasp rule and figure out the direction of the magnetic field line. It's going to be this way. So it's going to be to the right on the top. And I use my bangle again, like this. And once you have the magnetic field line, to figure out the magnetic field at a specific point, you just draw a tangent to the field line. So I want to find out what is the magnetic field at this point to the right side. I'm going to hold the conductor this way so I can hold it. All right, so I want to know what is the magnetic field at this point over here. So you have to imagine a tangent to this circle at this point. What would that look like? Well, I'm just going to tilt a little bit so that you can see it properly. If you draw a tangent over here, notice you can draw two tangents, one this way, one this way. But since we already know the magnetic field is going to run like this, the tangent has to be downwards. So the magnetic field to the right of the conductor is going to be downwards like this. Over here, I could have just rotated this bangle also. And notice when I come to this point, hopefully you can see the arrow mark points downwards. So what do you think would be the magnetic field direction at the bottom? Can you try and do this yourself now? Think about this. Pause the video and think about this. At the bottom, over here, at the bottom. Well, again, I'm finding this a little hard to hold. Again, I'm going to hold it this way. Fine. So if you come right at the bottom, again, imagine drawing a tangent over here. What would the tangent look like? Well, I'll tilt it a little bit so you can see. The tangent might be this way or this way. But again, since I know the magnetic field runs like this, the tangent has to be in this direction. Again, I could have just rotated that. And notice you can actually see the arrow mark at the bottom. It's in this direction. Now, doing it this way, it's fine if you have a prop with you, like if you have a bangle and you have an arrow mark attached to it. But what if you don't have access to it? Imagining this could be very difficult. At least it used to be difficult for me. So I'll tell you what I used to do when I didn't have any props. So again, first step, clasp it with the right hand, same steps. Now I imagine the magnetic field running like this. So you also try and imagine this. Magnetic field is running this way. Now, instead of a prop, I'm going to use my finger as an arrow mark, and I'm going to run in the direction of the magnetic field like this. Run in the direction. And now if I want to know the magnetic field at a specific point, I'll just stop over there. So for example, if I want to know what's the magnetic field direction at the right side, I'm just going to stop. And notice it points downwards. If I want to know what's the magnetic field at the bottom, I'm just going to stop. Hey, it's to the left. If I want to know what's the magnetic field to the left of it, it's upwards, and so on. And so that's how, using the right hand clasp rule and then running your finger along that field line, you can figure out the direction of the magnetic field at any point. So let's solve a couple of numericals now. A wire carries an electric current from west to east. Find the direction of the magnetic field at a point directly below the wire. Okay, so here we have to use east, west, north, south. So just to remember, this is north, this is south, right is east, left is west, up and down. So we have a wire that carries electric current that runs from west to east. So west to east is this way, if this is our wire. From west to east, electric current is in this direction. We need to find the direction of the magnetic field at a point directly below the wire. So we have to find somewhere below it. So pause the video and see if you can try to do it yourself first. All right, let's do this. So first step is to use your right hand and clasp this conductor this way. The thumb should point in the direction of the electric current, so it's going to be this way. And so the four fingers are telling me the magnetic field runs in this direction. I'm not going to use any props now. Let's just imagine this. And so the magnetic field runs like this way. And so I'm going to use my fingers to represent that. And since I want to know the magnetic field below the wire, I'm going to stop below the wire now this way. And so below the wire, the magnetic field is to the north. This is not up, this is up, this is to the north. So the answer is to the north. All right, let's solve one more. Suppose you are standing in your room and you find an electron moving from the ceiling to the floor, right in front of you. Find the direction of the magnetic field towards your right. All right, let's think about this. I'm standing in my room over here, and there's an electron that's moving from the ceiling to the floor like this. And I need to find out what direction is the magnetic field to my right side, over here. Now you may be wondering, where did an electron come from? Well, remember, an electron is a charged particle, and whenever a charged particle moves, it creates a current. And we know that current produces a magnetic field. And that's how there is a magnetic field, and we need to figure out what direction the magnetic field is on the right side, on my right side. So this is a little bit tricky because electron is a negative charge. So again, pause the video and see if you can figure this out. All right. The tricky part is electrons are negatively charged particles. So if electron is moving downwards, a negative charge is moving downwards, then the direction of the current is upwards. Because you may remember, electric current direction is the direction of positive charge, opposite direction of negative charge. So since electron is moving down, our current would be upwards like this. Okay, that's the only tricky part. And now we have to figure out the direction of the magnetic field over here. All right, so if you have not done it before, now would be a great time to again pause and see if you can figure it out. All right, first step is to use the right hand to clasp this conductor such that the thumb points in the direction of the current. And now the four fingers will tell me what direction the magnetic field is. And so it's telling me the magnetic field runs this way, like this. And so I'm going to use my finger to run it like this. Magnetic field runs this way. Since I want to find the direction on the right side, I'm going to stop on the right, and it's going to be this way. And so that is towards my north. So the magnetic field over here is to the north. So what did we learn in this video? We learned how to use the right hand thumb rule to give us the direction of the magnetic field. Basically, whenever you have a current carrying conductor, you use your right hand, clasp it such that the thumb gives you the direction, thumb represents the direction of the current, and then the four fingers will tell you what direction the magnetic field is.
The video that you saw, the first video shows the magnetic field around a straight conductor. That is, when electric current passes through a straight conductor, a magnetic field is produced around that straight conductor. Then what is the shape of that magnetic field? The shape of the magnetic field is concentric circles. You have studied about concentric circles. Concentric circles are circles with the common center but different radii. So here the magnetic field produced around the straight conductor has the shape of concentric circles, the center being the straight conductor. And the magnetic flux lines will be encircled around the straight conductor as concentric circles. Now the second video shows the direction of magnetic flux lines. So watch carefully the second video. That is, it shows the direction of magnetic flux using thumb rule. So what is this thumb rule? Thumb rule says, if you are grasping a straight conductor through which current passes by your right hand, such that the thumb represents the direction of current, then the other four fingers encircling shows the direction of magnetic field. See, it is very easy. Suppose, consider this is a straight conductor, and the two ends are connected to a source of current, or the two ends are connected to a battery. Now consider, suppose, first one, the current travels from, or the current is passing from the bottom to the top. So how will you find the direction of magnetic field? The direction of magnetic field is found out using thumb rule. That is, the thumb rule says, grasp the conductor by your right hand. How? By your right hand, such that the thumb indicates, here the thumb indicates the direction of current. We have already said the current is passing from the bottom to the top. So the thumb always indicates the direction of current. and the direction of the other four fingers. See that other four fingers are encircling in this direction. So this direction shows the direction of magnetic field. Now we can reverse it. Consider the current is flowing from the top towards the bottom. So how will you hold this? The thumb should be downwards. So you should grasp the conductor like this. The direction of current is downwards. And how are the other four fingers encircling? Other four fingers are encircling like this. So what is the direction of magnetic field? Magnetic field direction will be towards this side. So when the current is upwards, the magnetic field is like this. And when the current is downwards, the magnetic field will be like this. So this is rule known as thumb rule, Maxwell's thumb rule.